Welcome back to part 2 of our discussion on testing the difference between population means using independent samples in which the population standard deviations are, again, unknown. That's the key. Last video, we introduced sort of the theory behind how we're going to approach the situation utilizing the t-distribution in the t-test. But also noting that there's a lot of different formulas to use this time around. In this video, we're going to look at 2 examples and work through them in detail so that we can get an understanding of how this is going to work. Just like we saw in the last video, the examples for hypothesis testing involve a lot of writing. So I'm going to write a little bit smaller to save myself room. And I also want to take this moment to let everyone know that if you do end up solving some sort of a hypothesis test in the future, whether it be for homework or an exam or something else, you should be writing about as much as I'm writing in these examples. If you're cutting corners and failing to explain why things are working and where they're going, this leaves a lot of ambiguity. And the reader is free to sort of fill in the gaps however they see fit, and sometimes the way they see it and the way you see it don't necessarily match up. So be sure to take the time to write out what you mean what you say. Let's jump into this example though. Here it says that the results of a state mathematics test for random samples of students taught by 2 different teachers at the same school are shown below. We have teacher 1 and teacher 2, and the samples were taken randomly. And apparently the first sampling had a sample mean of 473 with a sample standard deviation of 39.7, where here we only sampled 8 students. And teacher 2 had a little bit different data, but of course a little bit of a higher sample size as well. However, we note that neither sample size is larger than 30, so we're going to hope that these populations are normally distributed. And the question is, can we conclude that there is a difference in the mean mathematics test scores for the students of the 2 teachers? Here we only sampled a few of their students. The question is the population mean different as well? We're going to use a level of significance of 10%. And here we see what we're looking for. Assume the populations are normally distributed. And here is a very important follow-up. The population variances are not equal. So that helps inform us sort of through that tree diagram from the last video. So I'm going to make a start. And again, I'm just going to follow this step-by-step process we talked about last time. So we're going to begin by verifying our information and writing down the claims. So let's take a look. The observation I'm going to make in the beginning is the following. We're going to write the following. Note that sigma 1 and sigma 2, these are the population standard deviations. These are not even mentioned in the problem. So that tells us that they're unknown. They are unknown. We additionally see that the samples are random. And the question is, are they independent? It's not explicitly noted, but of course, the simple fact that the population sizes are different is more than enough to argue that they're independent. So the samples are random and independent. Additionally, we have this important assumption that the populations are normally distributed. So the net result of all of this sort of preliminary observations is that indeed we're in the context of the t-test. So we can use the t-test. Now that we know what sort of context we're in, we can now begin with the hypothesis test. So we're going to write down what the claim is. What was the claim? Rereading through the problem, we see that the claim is that there is a difference in the mean mathematics test scores. So the claim here in quotes is that there is a difference in the mean. That's the claim being proposed. What that means is that if we wrote down the means as mu1 and mu2, the claim is that they're not equal. That is, that they're different. So if we're to write down the null and alternate hypothesis, the null hypothesis is then, of course, going to be the option that involves the equality sign. So that's going to be that the two means are equal. And the alternate hypothesis is going to be the opposite of that, which is that the two means are not equal. Where we see here that, of course, the claim is going to the alternate hypothesis. Now that we've written down what the claims are and we've observed what sort of context we're in, we can come back up to the step-by-step process, and we see that the next option we need to look for is specifying the level of significance, determining the degrees of freedom, and then moving toward use of the t-table. Remember that figuring out your degrees of freedom depends on whether the variances are equal or not. So that's what we're going to observe next. We're going to observe that the assumption is that the population variances are not equal. So we're going to say, since the population variances are not equal, we might remind ourselves real quick what setting that puts us in. The population variance is not being equal. We'll come back up here. Are the population variances equal? The answer here was no. So what that means is our degrees of freedom are the smaller of either the first degree of freedom or the second. So what that means is we're curious about which of these sample sizes is smaller. So we're going to say, since the population variances are not equal and the smaller sample size is N1, which is, of course, 8, we have that our degrees of freedom are N1 minus 1, which is, of course, 8 minus 1, which is a 7. So now we know what our degrees of freedom are. We can use our degrees of freedom, as well as the level of significance alpha, to then take a look at the t-distribution to find our critical values. Of course, that is somewhat dependent on the nature of the hypothesis test, which is related to whether it is going to be a one- or two-tailed test, which of course is informed by the symbol that the alternate hypothesis contains. So what we'll see here is that since the alternate hypothesis is that the mu1 is different from the mu2, that is, the important observation is the existence of the not equal to symbol, this is a two-tailed test. Of course, with the level of significance assumed at 0.10. That was given in the problem up here, right? So now we have the nature of the test, the level of significance, and the degrees of freedom. We can find our critical values. So we're going to come down to the t-table, which is attached at the end of the handout here. We're going to look at the two-tail category until we find our proposed level of significance, which is 0.10. Now we're going to go down column 2 until we get to a degree of freedom indicated as 7. So here is our proposed degree of freedom 7. We go down column 2 and we see that the overlap is right here at 1.895. Since this is a two-tailed test, remember, of course, just like we have down here, what that means is that the left tail is governed by negative t and the right tail is governed by positive t, where t is 1.895. So let's import that back into our problem here. What we'll find here is that by using, we'll call it maybe the t-table, the two critical values are negative t sub 0, which is negative 1.895, and positive t sub 0 is positive 1.895. And the rejection regions are everything to the left of the negative and to the right of the positive. So anything less than negative 1.895 and anything greater than 1.895. So now that we have our rejection regions, we now need to figure out what the standardized test statistic is so that we can compare it and figure out whether it does lie in the rejection region. That is, in context of this 9-step process, we have figured out up to step 6. Our next step is to figure out what this t-value is. But remember that this t-value is dependent on its denominator, the standard error, and that standard error, the formula for that changes depending on how our variance is compared. Because remember, based on the flowchart, if the population variances were not equal, which is the context of what we're in right now, then the standard error, the denominator of the standardized test statistic, follows this formula. So this is the information we're going to import. Let's do that now. What we're going to do is we'll find that the standardized test statistic is, well, the formula is always the observed difference, so that's x1 bar minus x2 bar, minus the hypothesized difference, which is mu1 minus mu2, all over what would be the standard error, but given the context of the variances being different, we know that this is equal to the square root of the sample variance over the sample size, plus the other sample variance over the sample size. And if we just plug in the values, we'll find that, and remember that x1 bar and x2 bar are of course given the context of the problem, so are s1 and s2. So if we're just going to plug in that information, we'll end up with 473 minus 459. That's the x1 bar minus x2 bar. Remember that in context of hypothesis testing, you always have the underlying assumption that the null hypothesis's equality is holding, which means there's this underlying assumption that the hypothesized difference is nothing. So that's minus 0 over the square root of, and in this case we'll get 39.7 squared over 8 plus 24.5 squared over 18. And if you compute all this and round to 3 decimal places, you should get 0.922. And so now the question is, how does this standardized test statistic compare with the rejection regions? And we see that this lies comfortably out of the rejection regions. So what that means is that since 0.922 is less than 1.895, what this means is that we do not reject H naught, which means there's somehow the null hypothesis is favored in this case, meaning that there's not enough evidence to support the claim, since the claim, of course, is the alternate hypothesis here. So just as we do every time, we now need to write out in English sort of what this interpretation means. So what do we find? we find that there is not enough evidence at the 10% level of significance to support the claim that the mean mathematics scores for the students of the two teachers are different. So this finishes off the first example of two that we're going to do in this lesson. And this goes through sort of the barehanded step-by-step procedure that one has to conduct in order to do a hypothesis test in the context of section 8.2. Note that a key observation is that here there was the assumption that the variances are not equal. If the variances are equal, some things change. The computation of the degrees of freedom slightly change, and of course the computation of the standard error down here also slightly changes. The next example is going to highlight some of these changes. Additionally, the next example is going to have us encounter a situation where our null and alternate hypotheses contain symbols other than the equal and not equal sign. Since, if I recall correctly, the example we did in section 8.1 was also one that used the equal and not equal sign. So it's important to take a look at a variety of different examples. That example is the following. A manufacturer claims that the mean operating cost per mile of its sedans is less than that of its leading competitor. So right off the bat, we have the claim thrust upon us that the mean operating cost of their sedans is less than its competitors. That is, mu1 is less than mu2. We conduct a study using 30 randomly selected sedans from the manufacturer and 32 from its competitor, and then we run some quick statistics. We get a pair of sample means, some sample standard deviations. Of course, we have the sample sizes we did. At a 5% level of significance, the question is, can we support the manufacturer's claim? And then we have a necessary assumption. Here, we're assuming the population variances are equal. This is notably different from what it was in the last problem. Just like we did before, we're going to begin by collecting our hypotheses to make sure that we're in the context of the correct framework. So what we're going to do here is we're going to note that in particular, nowhere in this problem are we told what the population standard deviations are. So we're going to note that sigma 1 and sigma 2 are unknown. The samples are random. And just like last time, the sample sizes, of course, are different. So that means definitely the sampling was done independently. So the samples are random and independent. And note that unlike the previous problem, in the previous problem, we did have this underlying assumption that the populations were normally distributed. We are not given that assumption. However, we don't need it because the individual sample sizes, N1 and N2, are each greater than 30. So therefore, we're still in good shape. So we'll say, and N1 is greater than or equal to 30, and N2 is greater than or equal to 30. So all of these hypotheses allow us to conclude that yes, we're in the context of section 8.2, and yes, we can use a t-test. So we can use a t-test. Now we want to write down our claim. What was the claim? The claim is the highlighted bit that one mean is less, that's the key observation, is less than the other mean. So the claim here is that mean 1 is less than mean 2. Just sort of putting that in air quotes so that we can sort of interpret it. So what does that mean as it relates to our null and alternate hypothesis? Well, the null hypothesis and the alternate hypothesis, what we want to say is that mean 1 is less than mean 2, but remember that the null hypothesis always gets the symbol with the equal sign. So the alternate hypothesis is then going to be the claim that mu1 is strictly less than mu2, and the opposite of that, of course, is mu1 is greater than or equal to mu2, where here the claim is on the alternate hypothesis. Now we want to move toward trying to find our critical values. That requires use of the t-table, which of course requires us to know our degrees of freedom. The degrees of freedom, the computation is slightly different depending on what the population variances look like. In this case, the population variances are assumed equal. So if we go back up to our flow chart, if the population variances are equal, then the degrees of freedom are the sum of the sample sizes minus 2. So we're going to do that. Writing it out explicitly, what we might write is the following. We'll say that the population variances are equal, so the degrees of freedom are computed by taking one sample size plus the other sample size and subtracting 2. In this case, 30 plus 32 minus 2, which is 60. Now, this number is a much larger degree of freedom than probably we've encountered so far. But nonetheless, as long as it's on the t-table, we're good to go. With that said, let's write down what our level of significance is and actually try to figure out what the t-table critical values are. Of course, that's going to be dependent on the nature of the hypothesis test, which is dependent on the symbol that the alternate hypothesis carries. So, since the alternate hypothesis is that mu1 is less than mu2, where the operative thing here is the less than symbol, we observe that this is a left-tailed test. In the context of the t-table, remember that being left-tailed simply means one-tailed. Being left-tailed means that when you look in the one-tail column, you're going to take the negative t, as opposed to the positive if it was right-tailed. We might also write here that parenthetically, and our level of significance alpha is 0.05. So, by the t-table, t sub 0 is equal to, well, now we need to find our critical value. So let's head over, let's import all this information into the t-table and see what we can find. So we'll delete the information from the previous problem. And what are we looking for? We're looking for a one-tailed test. We want our level of significance to be 0.05, so that puts us in column 2. And we want to come down all the way until we can find a degree of freedom of 60, which eventually we do find. Eventually it starts jumping by tens. So we want that row, and we said we wanted column 2. And here it is, our overlap is 1.671, where since we're using, as we see in the picture over here on the right, a left-tailed test, we want our t to be negative t. So our t won't be 1.671, it's going to be negative 1.671. So let's import that, that's negative 1.671. And the rejection region, since it's a left-tailed test, is everything less than that value. And the rejection region is any t value that's less than 1.671. So now we need to actually take the data from the problem at hand, convert it into a standardized test statistic, and then compare that to this proposed rejection region. The standardized test statistic, as we see in this breakdown, is still going to be the observed difference minus the hypothesized difference over the standard error. But remember, in the context of section 8.2 here, the formula for the standard error depends on what the variances look like. In the problem we're working with, we're assuming the variances are equal. So if we go to our flow chart, if the variances are equal, then the standard error is given as sigma hat times this square root bit. Where sigma hat, if we go back a page, is given by this complicated looking formula. So it may be useful in our problem right now to start by computing the standard error, which requires these formulas put together, then take that standard error, put it inside of our standardized test statistic, which then will compute the standardized test statistic. So in the space provided, I'm going to start by computing the standard error. The standard error in our context, well, it's always given the symbol S sub x1 bar, x2 bar, but for our purposes, because the variances are assumed equal, this formula is always going to be sigma hat times, we'll come back up here and import that result, it's sigma hat times the square root of 1 over n1 plus 1 over n2. So it's the square root of 1 over n1 plus 1 over n2. But sigma hat itself has a formula. Again, we'll import that. That's this formula right here. So if we import that, this formula is apparently equal to the square root of n1 minus 1 times s1 squared all over, well, plus n2 minus 1 times s2 squared all over n1 plus n2 minus 2. That's our sigma hat times the square root of 1 over n1 plus 1 over n2. So let's plug in all of our information for what this is going to be equal to. We're going to get n1 was 30, so we get 30 minus 1 times s1 squared, which is 0.05 squared, because that's our s1. Our s2 is 0.07, and our n2 is 32, so here I'm getting minus 32 minus 1 times 0.07 squared all over 30 plus 32 minus 2. So this is that sigma hat term times 1 over 32 plus 1 over 30. So I guess I wrote this backwards, but it won't matter. You'll get the same number at the end of the day. And if you compute this, you should get approximately equal to, if you round it, well, for this one, we're going to take this value and we're going to import it into the standardized test statistic formula. So probably I don't want to round too much. So I'll write out a lot of terms of this. Maybe we'll write out 0.0155416. So there's a lot of terms of that. So now that we have the standard error, we can come back up to our equation of the standardized test statistic right here, and we can plug in our value we just found for its denominator. So the standardized test statistic is Well, remember, it's the t, which is always going to be the observed difference, x1 bar minus x2 bar, minus the hypothesized difference, x1 or mu1 minus mu2, all over the standard error, s sub x1 bar minus x2 bar, where now we have all the relevant pieces. x1 bar was 0.52, x2 bar is 0.55. In the context of hypothesis testing, the mu1 minus mu2 is always 0. The standard error is what we just computed up above right here. So we're going to rewrite that as 0.0155416. And if you compute this and round it to, say, 3 decimal places, you're going to get approximately negative 1.930. So now sort of all the new difficult work is handled. The question is the age-old hypothesis test question, which is, how does your standardized test statistic compare with your proposed rejection region? And what we see here is that, in fact, this standardized test statistic is actually less than negative 1.671. So here we are in the rejection region. So what we're going to say here is that since negative 1.930 is less than negative 1.671, we reject the null hypothesis. What does that mean? What this means is that we are going to reject this null hypothesis, and since the claim was the alternate, this means that there is enough evidence to support the given claim. So let's write that out. The conclusion is that there is enough evidence at our desired significance level, at which alpha was 0.05, so this is the 5% level of significance, to support the claim. And what is that claim? That the mean operating cost per mile of the manufacturer's sedans is less than that of its competitor sedans. So here we have an example where we have actually yielded enough evidence to support a given claim. As you can see, the amount of work required for this problem was very similar to the amount of work required in the previous problem. And if you're looking at doing this sort of a problem on an exam or something, you should endeavor to write pretty much this much work in order to deliver your point. Now, this second example illustrates sort of the other side of the coin. In the first example here, we had a slightly different set of alternate and null hypotheses, but since we had the underlying assumption that the population variances were not equal, things changed a little bit. We also here assumed the populations were normally distributed, so our original hypotheses were a little different. Whereas in the example we're working in here, we assumed the population variances were equal, which changed our computations significantly, and we did not have the assumption about the normal distribution of the populations because our sample sizes were large enough. So these two examples, although lengthy, really highlight between the two of them the different sort of ways that a question from section 8.2 can be addressed. So this is where we're going to wrap up our conversation in section 8.2. The next lesson, section 8.3, we're going to continue our discussion on testing the difference between population means. However, we're going to move toward understanding what happens when the sampling that you encounter is taken instead of independent. What happens if we encounter dependent sampling, so-called paired or matched sampling? And we're going to figure out how that works. Until then, though, take a look at some of the homework that's available. Let me know if you have any questions, and I will catch you all in the next one.